hydrogen and green fuels for gas turbines. Let me introduce myself first. My name is Erik Zindel. I work for Siemens Energy. I've been in the company for 31 years approximately, working in a variety of all the different positions that you can imagine, mostly around gas turbines, combined cycle power plants, but as well a little bit of renewable generation. And in the last couple of years, the topic of hydrogen has become quite an important part of my daily job. I'm currently in the strategy organization, and I'm responsible for the decarbonization of gas turbines. That means the use of hydrogen and green fuels for gas turbines. I'm also part of a corporate-wide initiative called Power to X Field of Action. That means this is a corporate-wide initiative that determines the whole strategy on hydrogen of our company. And in addition, I'm also the project manager of the Hydrogen Academy, which is a corporate-wide training initiative on hydrogen topics. And I'm also giving, as such, regularly trainings on hydrogen, both technically and as well on the sales front. So I would like today to give you an overview about the use of carbon-neutral fuels in gas turbines. And first I want to give an overview about why is hydrogen a potential topic for gas turbines and how do gas turbines fit in the future energy landscape. Second, I'm going to concentrate very much on hydrogen itself as a fuel for gas turbines. As a third chapter, retrofitting of existing gas turbines to hydrogen operation. And then I will give one additional outlook into other decarbonized fuels like biofuels and hydrogen derivatives such as ammonia and methanol, and concluding then with a short conclusion and executive summary. This is not a very large audience today, but I would recommend keep the questions to the end, unless there are some very specific understanding questions that you could then ask directly. So first, I would like to give you an introduction into why hydrogen and carbon-neutral fuels. And I would like to begin my presentation with the main driver of all these activities, and that is global warming. You see here the evolution of the carbon CO2 emissions worldwide since 1960 to 2022. You see this graph has been increasing over time, and carbon emissions make up 2/3 of the total greenhouse gas emissions. And within that CO2 emissions, the power sector is the largest contributing sector. So it contributes 40% of all the emissions, CO2 emissions in the world are associated with electricity production, and that is the use of fossil fuels, whether it's oil, coal, or gas. But it's not just the power sector. We also need to understand there are other sectors that are also contributing to CO2 emissions. And we have industry with 24%, transport 21%, buildings with 10%, and some additional other small items. So the big question is, how can we decarbonize? How can we reduce the CO2 emissions worldwide? It's not just about the power sector. The power sector is our responsibility, but we also need to look into the other ones. And the way how we expect this is going to happen is by a concept that we call sector coupling. And the concept of sector coupling is quite simple. The idea is we have in the power sector access to green energy, mainly renewable energy like solar and wind. And we are not using this free sustainable energy just to power the power sector, but also give it to the other sectors in a way that they can use it. So the idea in the future is we're going to have green power as the center of all the energy in all the sectors. And that is, to a large extent, solar energy and wind energy. And a little bit of hydro, wherever that is available. All the other renewable energy types like biomass, geothermal, are just usually a very small contribution and only available in some areas of the world. So it's mainly solar and wind, and both are unfortunately intermittent. They cannot be produced when they are required, but just when the sun shines and when the wind blows. So the idea of sector coupling is to provide this sustainable energy to all the other sectors, whether it's industry, mobility, agriculture, you name it. And the best way to do that is by electrification. So the more you electrify other sectors, the more you can reduce the use of fossil fuels in the other sectors. Have a look, for instance, at buildings, heating and cooling. This can be easily achieved with direct use of electricity, whether it's for air conditioning units or in the colder climates with heat pumps, displacing natural gas, for instance. Then we have, in the mobility sector, we have the possibility of using electric cars, battery cars. By the way, a much more efficient way of driving a car with electricity than with an internal combustion engine. We can also use it for rail applications, for trucks. Obviously, there are some limits to electrification. If you look, for instance, at aviation or marine applications, doesn't really fit very much. So we're not going to electrify the Oman Air flight from Muscat to London, Heathrow, or even to New York. That's not going to happen, unfortunately. So we need energy as well as some other cases. Nevertheless, in the industry, we also have quite a lot of possibilities to use electricity instead of fossil fuels. Think about all the different heat applications where we have boilers, where we're using fossil fuels. Those can easily be transferred to electricity as well. But as I said, there is a limit into what we can do with electrification. And then it's when hydrogen comes into play. So the idea is then to use this renewable electricity, create hydrogen out of it, sustainable hydrogen, and that hydrogen itself can already help me to decarbonize other sectors. Think about the steel industry. The steel industry can easily be transformed from the use of coke to the use of hydrogen to produce steel out of iron by means of direct reduction of iron. So using hydrogen can then displace coke, which is, by the way, one of the most CO2 intensive industries that we have in the world today. Hydrogen could also be used in mobility, although for the mobility applications, the use of hydrogen will probably be limited to some trucks, some special applications. The typical private cars, small delivery trucks, those will be much better off with the use of electricity, with battery cars instead of hydrogen. But nevertheless, there is a possibility of using some hydrogen as well for mobility applications. And finally, when hydrogen is not able to be used to decarbonize the sector, we have to look into hydrogen derivatives that are products, compounds produced out of hydrogen. And one of them, a very common one, is e-ammonia. We can easily synthesize ammonia from hydrogen, and with green hydrogen or e-ammonia, we can then, for instance, displace ammonia produced out of natural gas, which would be then a total carbon-free ammonia. And that helps me to decarbonize the fertilizer industry and decarbonize as well parts of the chemical industry. And finally, we have all the topics of e-fuels, which are hydrocarbons synthesized out of hydrogen. And this can be used, for instance, to decarbonize all those sectors that are easy or difficult to decarbonize, like aviation and shipping, by use of hydrocarbons synthesized from hydrogen. That means, for instance, methanol, which is one of the easiest compounds to be synthesized from hydrogen. And from methanol, then I can go over and synthesize other e-fuels, such as diesel, gasoline, jet fuel. And with that, I can then provide even a fuel which is very comparable to the existing ones, so that they can easily be blended into the existing fossil fuels, and over time I can increase the ratio of green fuels until I finally achieve 100% decarbonization. And that helps me at the end to decarbonize as well the Oman air flight to London Heathrow in the future. And with that, we can as well synthesize more other components to be used in the chemical industry, for instance, all the plastics. And that's a little bit the idea of the sector coupling. It's really putting the renewable energy at the forefront of all the energy, trying to electrify as much as we can. Where electrification doesn't work, let's move to hydrogen. Where hydrogen doesn't work, we have to go to hydrogen derivatives. And with that, we can probably decarbonize 95, 98% of all the sectors worldwide. So looking at the future energy landscape, and this is a picture of how an energy landscape might be looking like in 2050 or so, fully decarbonized. As I said, we have renewable energy being at the forefront, at the center stage of all the energy. As I said, it's mainly solar and wind, which means there will be times where there is an oversupply of green electricity and other times where there's a lack of green electricity. Well, every time we have sufficient electricity, one can use that directly in all the sectors that need electricity. Potential surpluses, I can then convert into hydrogen in electrolysis plants, and then I can get green hydrogen. This green hydrogen I can use directly as well for all the sectors that use hydrogen. And then I also have the area of heating and cooling, buildings mainly, but also industry, where I can easily use heat pumps. And heat pumps have the big advantage that they're much more efficient compared with a conventional burning of fossil fuels. And then I can also use the green hydrogen to produce the derivatives. E-ammonia through the Haber-Bosch process, which is a very established process to produce ammonia. And we have different hydrocarbon synthesis to produce all the e-fuels. For the Haber-Bosch process, to get the ammonia, that means an NH3 molecule out of H2, I would need the nitrogen atom. And the nitrogen I can get from an air separation plant, also standard technology. And for the hydrocarbons, synthetic hydrocarbons, obviously if I want to get a hydrocarbon out of hydrogen, I need the carbon molecule. And for that, I need a sustainable source of CO2. And a sustainable source of CO2 could be either carbon capture from an inevitable emissions, could be even better carbon capture from a biomass power plant, or in the future, very much under consideration also in our company, direct air capture, which is getting the CO2 directly out of the air. It's still a very expensive technology, but over time we expect this to become cheaper. And by using the sustainable CO2, I'm still producing a hydrocarbon which I will be burning in, for instance, in an airplane. So it's not really decarbonized physically, but it's carbon neutral, and that's what we want because the CO2 then always is in flow and we're not adding additional CO2 to the atmosphere. And synthesis process, I said, many different possibilities. Methanol is very easy to synthesize. Methanol can be easily used as a substitute for gasoline and diesel. But also jet fuel, very important. It's probably one of the largest future markets for hydrogen derivatives, jet fuel. Because for airplanes, the big issue of needing a very high density of fuel in an airplane, you have very limited amount of volume at your disposal in an airplane in order to drive the airplane. Remember that you have to carry all the fuel with you all the flight. Electrification doesn't work. The batteries would simply be too large. You can maybe electrify a small general aviation aircraft, a typical Cessna, 4, 6, 8 passengers. Maybe long-term, a small regional 20-passenger airplane, but only for 200, 300 kilometers. So apart from island hopping, you need to go to a chemical storage of fuel. And hydrogen could be a possibility, but hydrogen comes with a disadvantage that you would need to liquefy it. And you also still have the issue of very high or very low volumetric energy density of liquid hydrogen compared with jet fuel. And that is why probably the use of synthetic jet fuels, we call that SAF, Sustainable Aviation Fuel, will likely be the option to go. Methanol, by the way, is today considered one of the prime contenders for the decarbonization of shipping industry. And we see that most of the large shipping companies like Maersk, MSC are already switching towards methanol as the future fuel. They're already laying down the keel on new ships that are fuel flexible and can also run on methanol. And finally, we also have all the area of e-chemicals. So all the olefins like ethylene and all the compounds that you need to run the organic chemistry. Think about everything what we see today is mostly made out of plastics. We also need to decarbonize the plastics work. And we can easily as well synthesize ethylene from hydrogen. And with that, we can have also a decarbonized organic chemistry. Very important as we talk about the sector coupling, which is we're coupling energetically all the sectors more and more together. We need at the same time to decouple the time of use and production of energy. And that is why storage of energy becomes so important in the future. If we look at heating and cooling, that's fairly easy to store because I can simply put a tank of hot water or cold water, and then I can run my heat pump at those hours of the day where I have a surplus of energy. Think about here in Arabia, in the Arabic Peninsula, you will have a very high amount of photovoltaics during noon, but you want to use the air conditioning when you go home in the evening. And then you can run the air conditioning unit at noontime at very cheap electricity prices, store the cooling in a tank, and then you have the air conditioning available in the evening when you need it. Hydrogen also needs to be stored, and the way to store hydrogen is on large scale in a large pipeline system together with underground storage. Underground storage can be different types of storage that we could envisage. It depends on the geology of the different countries. You can have salt caverns, you can have as well depleted gas fields that you convert to hydrogen storage. It's the only way, and by the way, it's very important as well to have large amounts of hydrogen storage because the production and the use of hydrogen, because it's fairly dependent usually in the case of green hydrogen of renewable energy, comes with a large seasonality. So you need to go into seasonal storage of energy. And the underground cavern storage is an easy way to do it. It is not cheap, but it's also not very expensive if you look at the total costs of the whole energy system. All the derivatives come with usually, most of the cases, liquid form, so they're easily to store in tanks. That's fairly common and nothing special. When we talk about now electricity, storage of electricity, it's a very important topic. I said we're going to have surplus and a lack of electricity depending on the hours of the day and the month and the year. For short duration of storage, batteries are the best option. They have a very high cycle efficiency of 95%. So ideally suited, for instance, to push the peak of the PV from noon to the evening. But when it comes to storage of more than 3, 4, 5 hours, batteries are not really very cost effective. And it's definitely not a possibility to use batteries to get into a week, month, or even seasonal storage. For that one, we have to use green hydrogen and re-electrify it in gas turbines and combined cycles. And that will provide us the possibility to get 24/7 over the year renewable electricity, 100% decarbonized. So storage of electricity, short-term is batteries, but long-term seasonal re-electrification of hydrogen. And that is where the gas turbines running on hydrogen come into play. This slide shows what we call the residual load. Residual load is effectively all that part of the load demand that is not covered with renewable energy. This picture shows, in this case, Germany. This was 2 weeks in January 22. You see that we have this red curve is the demand, and then we have renewable energy, we have some biomass, we have hydro. The blue one is wind, onshore and offshore. So you see wind sometimes, there's a very high amount of wind, but then we have days where there's barely any wind. And then we have as well a little bit of solar PV. Obviously, this being January, the PV production in January in Germany is very small. And all the gray part is what we call the residual load. That has to be provided with other forms of electricity. Today, mainly combined cycle plants, and in Germany also some coal plants. Now let's look into the future. Let's think about a system that is largely decarbonized. And let's assume that we have in Germany a total coverage of 86% with renewable energy. We do a simulation, so we just increase the amount of PV and wind. And then we're going to see that there will be some days where there is a surplus of electricity and other days where we still have a lack. And that's the gray part. That's what we call the residual load. But also in this case, we need really to look into how can we fill that gap in the future. Obviously, different countries will have different load profiles, but in general, using just wind and PV, you will always have those periods of the year where there's not enough renewable energy. And these periods can be quite large, by the way. And if we look now at some extreme situations, this is also Germany. January 2017, this is 4 weeks where we barely had any wind and any solar. This is an extreme. But these extremes tend to happen and will also happen in the future. Even more, if you ask some climate experts, they will tell you that with increased global warming, we're going to see more and more periods of extremely stable weather conditions, which means periods with large residual load demand may increase in the future. This was 4 weeks of nearly no wind and no sun. If we do the same simulation with 86% renewables coverage, something that we can expect in 2040, 2045, we see that over these 4 weeks, we barely have only a few hours with surpluses. So batteries won't work, not at all. We need power plants that are capable of dispatching decarbonized power over several weeks, nearly in baseload. And that is where gas turbines and combined cycles have a role to play. And it's, by the way, the most efficient way to do it. Otherwise, trying to get the power from the neighbors will also not work because the neighbors will probably have exactly the same meteorological conditions. And even if you think about, well, maybe I can import electricity from 1,000, 2,000 kilometers away. Remember that usually wind and solar is associated with lows and highs, and these tend to have 1,000, 2,000 kilometers set apart. But even in those cases, assuming that you have even a copper plate across the continents, and it's free shifting of electricity, even that you would still calculate a very large demand loss. So we need to look into running gas turbines and combined cycles with a decarbonized fuel. One additional point, maybe not so much of interest here for Oman, but for many other, especially industrialized countries with lots of heat demand for industries and as well cooler climates. I said that heating will be done in the future with heat pumps. That means with electricity. Well, if we don't have renewable electricity to run the grid, we're not going to have renewable electricity to run the heat pumps either. So we need as well to provide heat demand in these parts of the year. And that means what we call the residual load. All this grayish area here is also at the same time the residual heat loss that we have to cover up. And that is why also CHP, cogeneration, production of electricity and heat at the same time in combined cycle power plants, will still remain very important in the future. In Oman, the situation obviously is a little bit different, but you will also have situations where there is a longer period of time where you have large demands of power that you cannot really cover completely with batteries or with solar and wind. And a combination of maximizing the renewables, maximizing PV, maximizing wind, plus some residual load with decarbonized fuel like hydrogen will probably give you the lowest generation costs in the country over long term. Residual load in Germany, we expect 20–25% of the hours of the year will have gas turbines running on hydrogen. The rest will be purely renewables. In Oman, due to the big advantage of excellent PV conditions all year round and the possibility to couple it very good with batteries, the capacity factor for this residual load plants will be probably lower, maybe in the 10–15%, but you still need them. So, as said, we need to decarbonize the residual load. Residual load today is mainly combined cycle power plants. And question is, well, which fuel? In general, hydrogen is the best solution. It has some advantages over other cases. Obviously, hydrogen is always cheaper than any hydrogen derivative because every hydrogen derivatives will come with additional capex investment to synthesize those e-fuels and with efficiency losses. It will allow a full decarbonization. You can also think about biofuels, and I will talk about biofuels later, but biofuels will not give you 100% decarbonization. With hydrogen, especially green hydrogen, you can achieve that. And finally, and that's also extremely important, if you have the possibility to use hydrogen in the power plants during the residual load event, you can overbuild the renewables in the country. And overbuilding renewables, that means building many more PV and wind parks than you would usually require, gives you two advantages. First, you get the excess energy that you can convert into hydrogen in order to be re-electrified later. And as well, it increases the amount of hours that you can run on renewable power. So instead of having 20, you only have 10% residual load. That will, over long term, reduce the cost of total generation in the country. Disadvantage for hydrogen is you need a pipeline. You need a pipeline connection. If you want to run a gas turbine with hydrogen, you can only do it if you have a connection to a pipeline and you have sufficient hydrogen in the pipeline system, including the underground storage, because you cannot run a gas turbine with hydrogen stored locally. If we think about a large gas turbine, 4000 F, ones that are installed in Barca and Sohar, if you want to run one of these units with 100% hydrogen, think about truck loading, you would require a truck coming to the power plant every 30 or 40 seconds. Full truck load of hydrogen. It's not going to work. You need the pipeline. And you need as well the large cavern storage. That is to compensate for the seasonality of renewables and the residual load demand. You tend to have a much higher consumption of electricity in one part of the year, lower in the other one, and the renewable electricity production is exactly the opposite quite often. So you need this hydrogen storage for seasonal storage. And we know that there will be locations in the world where a hydrogen pipeline will not be available. Think about locations that are far away from any potential hydrogen backbone network. Good example is in the Far East. We have Japan, we have Korea, South Korea, we have Taiwan. They don't have sufficient renewable energy. They have bad conditions for renewable energy. So, and because they are effectively islands, they cannot get hydrogen from somewhere else. Well, they could maybe try to get hydrogen via pipeline from one of their neighbors, but usually if you only have one neighbor and you're not on very good terms with that neighbor, it's not going to work. Then regions with chronic deficit of renewables. That's not the case for Oman, but it's the case, as I said, for Japan, Korea, Taiwan, also the tropics in general. They tend to have very bad wind conditions and as well not much sun because it's always cloudy. And also islands. In islands, you cannot build up a large backbone network, and for geological reasons, you may not be able to put a cavern, underground cavern. So in those cases, we need to look into alternative fuels as well. So, and this is a slide showing all the possibilities of how you can run a gas turbine, a combined cycle in a decarbonized way. And all of these options are available, and there's not one size fits all. It's really depending on the local situation. You might have to go to one or the other solution. The first possibility is you continue to run on natural gas, have a natural gas pipeline, and you run a gas turbine combined cycle with carbon capture storage. That's one possibility. Carbon capture, not an easy technology. It's a rather expensive one, but it works. It's a very capex intensive and also opex intensive because you're losing 7–8% points of efficiency in the power plant. But in locations where you have bad conditions for renewable, that means a large amount of hours of the year where you have to run these combined cycles, and you have cheap natural gas, and you have the possibility of storing the CO2 underground, then probably natural gas with carbon capture storage will be the cheapest alternative. Then I have said we have hydrogen. Hydrogen, as I said, requires a pipeline, and then we can run hydrogen on a 100% hydrogen gas turbine. Hydrogen can be produced either from renewables, that would be the green hydrogen, or it can also be produced with natural gas, with carbon capture, blue hydrogen. The gas turbines in themselves are color agnostic, so they don't care where the hydrogen is coming from, and blue and green hydrogen are chemically exactly the same. It's just a different origin and maybe a different carbon footprint. With blue hydrogen, you can get not to 100% down in terms of decarbonization, because you always have to take into account the losses of the upstream losses of methane to the atmosphere, and as well the carbon capture process not 100% efficient. Depending on the conditions, somewhere between 65 and 85, 90% decarbonization you can achieve with blue hydrogen. And as I said, some areas will not be able to use hydrogen or don't have access to natural gas either. And then you have to look into hydrogen derivatives. That could be ammonia, methanol, or other e-fuels. In general, we're going to see both ammonia and methanol as the most attractive derivatives of hydrogen to be used in gas turbines. And we have as well biofuels, which I'm going to cover as well later in a moment. The big advantage of all these derivatives and biofuels are that you can easily store and transport them in a liquid form, and that overcomes the situation of issues with gas pipelines. So now I'm going to explain a little bit more about this 100% hydrogen gas turbines and as well other cases. Let's first look at the use of hydrogen for a gas turbine. This graph shows a little bit how much hydrogen do you need to run a turbine. And let's be clear, it's huge amounts. If you want to run different cases, different peaker plants, flexible operation plants, or reserve power plants, depending on the operational profile, and if you want to run it on green hydrogen, that means you need electrolysis to produce all that green hydrogen. You need to store it. And as an example, for a peaker plant that runs only for 4 hours a day, you would have, over the year, 1,460 operating hours, and you would need a 17-ton storage capacity. 17 ton, and this is, by the way, for a power plant of 90 megawatts only. 17 ton equals around 50 truckloads, just to give you an idea. And you would need, in order to replenish that, 4 electrolysis totaling 70 megawatts. We're using our ELISA 300, which is our standard electrolyzer technology that we have in-house, as an example. So you would require 70 megawatts of electrolysis that you would then run for a 13 hours full load operation in order to get the required hydrogen to run this turbine for 4 hours. If you do 6 hours every second day, you're already at 26 tons of storage capacity. If you want to go into different operation days, 1 day, 2.5, 7 days, you see that quickly the amount of hydrogen storage increases significantly. That's where you really have to go into the seasonal storage, because that's effectively what we're going to see. The small peaking plant, 4 hours, we might probably be better off with batteries, but not if we have longer periods of lack of renewable power. Pipelines, I said, is a very important part of this equation. This graph shows what is going to happen in Europe. In Europe, we have a large initiative called H2 Backbone. And the intention is to build over the next 20 years a large hydrogen infrastructure with pipelines. And most of these pipelines, new pipelines, will effectively be rebuilds of existing gas pipelines. And so the idea is to convert existing natural gas pipelines to hydrogen pipelines, and that can be done quite easily. You don't need to change the pipe itself. You only have to change mainly the compression stations, everything what's above ground. And the big advantage of conversion of gas pipelines is that usually a gas pipeline is not just one pipe laid down under earth. It's usually a bundle of 2, 3, 4 pipelines in parallel, where you can easily isolate one line, convert it to hydrogen, and then you still have the natural gas pipeline and have a new converted hydrogen pipeline. And if you do it intelligently, then you can build up a complete network with 70–80% reconverted pipelines, and only the yellow ones, this would be newly built hydrogen pipelines. And the idea is to connect over the next 20 years the most important users and producers of hydrogen together. And the large users obviously will be steelworks, and it will be power plants. And the big advantage of such a large hydrogen network is it will also make use of imports. And the plan is effectively to use large amounts of imports, because Europe, with the huge amount of energy requirements, will always be energy deficient. So Europe will need green hydrogen being imported into the country. And we are looking very seriously at Northern Africa, the Maghreb area, Morocco, Algeria, Tunisia, Egypt, also near the Middle East. Even the Arabian Peninsula is within reach of hydrogen pipeline network from Europe. So over time, I do expect that large hydrogen pipelines will connect the Arabian Peninsula into Europe up to around 3,000–4,000 kilometers. The direct transportation of hydrogen in the pipeline is still cheaper than using a hydrogen derivative like ammonia or even liquefied hydrogen. So that's the long-term vision. The pipeline will allow for large amounts of imports and will also connect the underground storage, because you cannot build storage everywhere. It depends on the geological conditions. And we know, for instance, that salt caverns, a very good area, is something that you see usually in central northern Europe only. So you need to have the access to the hydrogen caverns as well in the future. So let's now look into hydrogen as a fuel for gas turbines. Hydrogen as a fuel for gas turbines is a rather mostly a new thing that is coming up, and we cover here everything. The use of green hydrogen, where we use renewable energy, convert that into hydrogen, store it in a pipeline and underground cavern, and re-electrify it later. We can as well use blue hydrogen, and there are as well a few cases where we still have some gray surplus hydrogen, for instance in refineries, that we can also use to re-electrify. Important to understand when we talk about hydrogen and gas turbines is that if we look at the complete chain from renewable energy through electrolysis, through compression and re-electrification, we have a cycle efficiency of usually a little bit more over 35% only. We're losing 2/3 of the energy across the way, which is a very large amount of energy losses. It's a very low efficiency, which means that if you can make use of batteries, you use batteries. But the issue with batteries is over 4, 5, 6 hours, it's not going to work. So you need to go into this re-electrification of hydrogen. It is not very efficient, but it's the only way, or there's still the most acceptable way that we have to provide 100% decarbonized power. Remember that in the future, this renewable energy will become extremely cheap. It is already very cheap. So we're losing, obviously, lots amounts of energy, but energy that doesn't cost too much. At least much less than what a fossil fuel costs today. So it's important to understand we have these large losses, but over the total year, the combination of 80% extremely cheap renewables and 20% of rather expensive residual load demand will still be probably the cheapest overall electricity generation costs. And one thing I would like to mention as well, over those times where we have a lack of renewables in the system and we have to run hydrogen power plants, you will also want to look at demand-side management. The idea is really to move the load a little bit to those hours of the day where you have more renewable power. So demand-side management will become very important as well in the future. It's not just about the demand side is fixed. Depends on what the people want to consume. Now it's really we have to convince consumers to use the electricity in a more intelligent way. We cannot move everything, but 15 or 20% of the electricity consumption we can at least move within 24 hours. Think about this use of air conditioning. We can easily use air conditioning during the noontime, store that cooling, and use the cooling then later when we come home. Okay, if I want now to burn hydrogen in a gas turbine. Hydrogen as a fuel in a turbine is not an easy thing to do. It is a very nasty fuel, to be honest. There are a couple of challenges associated with the use of hydrogen. You see them here on the upper left. The first one is we have something that we call hydrogen embrittlement, which is hydrogen attacks some of the steels, which is something that with a good selection of material we can handle. Then we have a lower volumetric energy content of hydrogen. So hydrogen is a gas that per volume has a lower content of energy compared with natural gas. On a mass on a mass, it has a much higher energy. If you compare it with the mass, yes, but on the volume, and that is usually what counts in a technical system, the energy content is lower, and that means we require larger flows of the fuel. That means the pipes have to become larger. Easy to do if we build a new power plant. For an existing one, it's an issue because we have to then make sure that the larger pipes really fit into the power plant. Then we have a higher diffusivity of hydrogen. Hydrogen is a very small molecule, and a sealing that is tied to natural gas may not be tied for hydrogen. So we have to change the seals, the flanges. We may have to go more into welded pipes instead of bolted flanges. Also something that, if we know it, we can easily do for a new plant. But then we have two really hard issues. The first one is hydrogen has an extremely high reactivity and very high flame velocity. It's around 8, 9, 10 times higher than natural gas. So it is a fuel that is extremely easy to combust. It has a very low temperature, ignition temperature. It has a very low ignition energy, and it has a very high flame speed. And that means the current burners that we are using in natural gas turbines don't work any longer. Because you know maybe that we have what we call premix burners, and the premix burners work in a way that we are injecting inside the burner the fuel. We're mixing it with combustion air, and inside the burners we make sure that the velocity of this mixture of air and fuel is higher than the flame velocity. And with that, once this air-fuel mixture leaves the burner and gets into the combustion chamber, then it slows down, and then we have a stable flame front inside the combustion chamber, and that's where we want to have it. If we have now hydrogen as a fuel, and we put it into a natural gas burner, the flame velocity would be much higher. The flame would eat itself up into the burner. That's called a flashback, and it would immediately destroy it. So we need to design a complete new type of burner. We can use existing burners with some hydrogen blends, and you see here lower the flame speed of hydrogen and natural gas mixture from 0 to 100% is not linear. It increases over time, and it's the last 20–30% where you really have a very high increase of flame speed. And you see as well the flame itself gets shorter and moves much closer to the burner the higher the hydrogen concentration. So within this area, 10 to 50, 60, 70%, we can still make use of the existing natural gas burners, but when we really want to go to 100%, we need a complete new burner design. And burner design is not something that's very easy, because we're talking about physically a situation where we have a combustion in a highly compressible stream of flow. We have aeroacoustics as well, so this is an area that we cannot model theoretically yet. We have Navier-Stokes, we have wonderful simulation tools, but we cannot really model theoretically what happens inside of the combustion chamber of a turbine under these high pressure levels, high temperatures, extremely high flows of air and gas, and we have this aeroacoustic, we have chemical processes happening in the stream. At the end, for our engineers, that means we have to try to model it as close as we can, but then we have to test. So we are using high fidelity computational fluid dynamics, but at the end it's really about testing, testing, testing. So we need to build different burners. We have to test them in a burner test. And usually what happens with these tests, sometimes they go quite well, and other times they're not going well. It's sometimes you can't really feel, it depends on the moon whether a test works or not. It's very, very difficult to predict what's going to happen, so we always have to go back to the drawing board. So it's always a cycle of theoretical modeling, building new burners, and for that we're using 3D printing, additive manufacturing, and then we are using usually our combustion test centers. We have one in Berlin, we have one in Sweden. That's where we test the burners, and once we have the burners, we have to go into the turbine tests. That makes another problem. Turbine tests you cannot do everywhere because you need, again, a hydrogen pipeline, and there are not so many hydrogen pipelines in the world. And especially for larger turbine types, it is an issue. Smaller turbines type you can easily still do with some local storage, but once we go, for instance, into a large turbine, even one burner consumes around 100 megawatts of thermal energy. That's a huge amount of energy, and the amount of changes that we have to do to our testing facilities and adding hydrogen storage is massive. It's really a significant investment. So one important topic when I talk about hydrogen burners is, you know, that there are two ways of reducing NOx emissions. The first one is what we call DLE, and the other one is WLE. So dry low emissions and wet low emissions. Dry low emission is really you try to design the flame in a way that you don't have a significant amount of thermal NOx production, while in wet low emission you are using water injection or steam injection to control the NOx. In general, in the past, all the manufacturers used wet low emissions, which was easy to develop, gave a more stable flame, and had an additional advantage that you got a higher power output in the turbine. Disadvantage was you have a very high water consumption, and you need demineralized water, and usually the water that you use for wet low emission is as expensive as the fuel, and especially in regions here like Oman, that is a definitely no-go at all. You cannot use these amounts of water. You have as well higher capex for water treatment and injection. You have a lower plant efficiency, means higher costs of electricity. You have still higher NOx emissions compared with the DLE mode, and higher maintenance costs. So all the manufacturers have gone to DLE systems in the past, and for hydrogen, that's also what we are doing. We're not looking at wet low emissions. Some of our competitors do, but we are developing hydrogen burners with DLE. They have the big advantage, you don't need water. You have a higher efficiency, lower costs of electricity, lower NOx emissions, higher component lifetime. Disadvantage, it takes more time to develop. It's not so easy. But for us, we're not developing wet low emissions. We're directly going into DLE mode because that's the only thing that our customers at least want to see. So what do you need to change if you want to switch to hydrogen? It's really not only about the gas turbine itself and the burner. It's also what happens outside of the gas turbine, in the package, in the power plant. Obviously, the burners and the combustion chamber is a very important point. And depending on the amount of hydrogen that you want to co-fire, the higher the hydrogen content, the more changes you have to do. From around 50 to 70%, you have to go to a complete new burner design. Before, you may use existing burners, but adapted. You have to do changes to the combustion monitoring system. Then, obviously, the fuel supply system, everything that's upstream of the gas turbine needs a complete look. That includes switch to stainless steel. It includes increase the diameter. You also will need likely a purging system because once you shut down a turbine, you need to purge the lines from hydrogen because you cannot really start so easily with pure hydrogen, so you need a secondary fuel as well. You need changes in the control and protection systems. Important as well, if you go over 20% hydrogen in the fuel, you have a different gas group classification. So your fuel complies then with gas group 2C. According to NFPA, that's NEC 500 Class 1 Division 2 Group B, means you need explosion proof. So every part of the power plant that may see a leak of hydrogen has to be built explosion proof. And that is a big issue for the electrical side. And then we have to look as well at SCR systems, because with NOx emissions and hydrogen, you do have a topic as well, or two issues. The first one is you have a slightly higher flame temperature with hydrogen. That means the production of NOx will increase compared with natural gas. And also there is an issue with the ppm measurement, and I have a slide in a moment that I'm going to explain why we're also going to see more NOx emissions, at least on a ppm level when using hydrogen. And then we also have to look at OEM procedures like leak checks. I said as well, startup at the moment, we're still expecting to run a start on a conventional fuel. This is because of the issues of ensuring a stable flame up situation with hydrogen. It's very difficult. There may be a situation where in a start with 100% hydrogen, we may go to a flashback, and a sustained flashback where we cannot get out of. So at the moment, we're still expecting to start on a conventional fuel. That can be natural gas, it can be also LPG, maybe in the future as well, methanol. So for the time being, we're still expecting a secondary fuel, but it's only a limited amount. So this is an amount of fuel that we can still handle inside a tank, for instance, like LPG. So this slide shows what we can currently offer today as blending ratios in new turbines. This is our complete portfolio of turbines, from the very small ones to the very large ones. You see that for the large heavy-duty turbines, we're already at 30 to 50%. We always talk volume percent, by the way. So 30 to 50% equals just a CO2 reduction of 11 to 23%. Remember, lower volumetric density. 50% sounds like you have gone half the way. No, you effectively only have gone a fourth of the way. On the intermediate size turbines, we're already at 75%, what we can offer. It's all dry, low emissions. There's one turbine that can already run at 100%. That's an aeroderivative, A35, but in this case, we would need water injection. That is something, as I said, we don't want to do in the future. So all our future hydrogen burners will be DLE only. And for the smaller turbines, we're again at 30%. And the goal is now, over the next couple of years, to move all these figures to 100% as soon as possible. And for that, we have a roadmap. You see that we began to work on hydrogen already since nearly 20 years ago, beginning first with the use of different blends, increasing the amount of hydrogen combustion. By 2019, we centralized all the hydrogen activities around gas turbines. In the past, we had different engineering locations with different frame types. Everybody had their own hydrogen strategy. 2019, we decided we're going to have one technology that we will test in one turbine, and then scale up to all the different turbine frames that we have. So far, we already achieved to get 100% already in 2019, and 2023, we had the first real commercial test of a 100% turbine. And officially, we have promised to deliver 100% turbines until 2030. Effectively, we expect that in the next few years, we're already going to be able to offer commercially 100% turbines. Not all of them. We begin with the most important frames. And by 2030, we're going to have several frames already with 100%. And over time, then we're going to increase the number of frames with 100%. This is a slide showing all our references around hydrogen combustion, and this is only a slide with turbines that are really running on a combination of hydrogen and natural gas. We're not showing syngas operation, because you know that things like coal gasification, you have as well high hydrogen contents, but in this case you also have a high CO content, and carbon monoxide really reduces all the nasty effects of hydrogen combustion. So burning a syngas is very simple with 50% hydrogen, but burning a mixture of 50% hydrogen with natural gas is a very difficult task already. So this is only pure mixtures of natural gas and hydrogen. Some of them are already in operation. Some of them were just testing for a couple of hours. But I want to show you some examples, both tests and commercial operation. The first one is our high flex power. This is an existing cogeneration plant in central France that already had a cogeneration plant based on an SGT 400, which is a 13 megawatt turbine. And in a large project, heavily subsidized by the European Union, and we had lots of different partners as well, we converted this power plant into a demonstration case for 100%. So we added one of our electrolysis units, an ELISA 200, a compressor. There is a local storage that, not a very large one, but at least a storage that could give us a couple of hours of operation. And then we changed the turbine, the core of the turbine, to a new core with the new burners that we have developed. And over 2 test campaigns in 22 and 23, we have been testing these new gas turbine burners with different blends of hydrogen and natural gas, concluding in September last year with a demonstration of 100% in DLE mode and running for several hours. Not too many hours, unfortunately, because we had only a limited amount of storage available, and because this is just 1 megawatt electrolysis, we're able really to empty the tank extremely quickly, and then it took us 1, 2, or 3 days to fill the storage again. And we also had only a very small testing window of 2 weeks in total, because we're only allowed to use this plant during the vacation time of the paper mill. Otherwise, the rest of the weeks of the year, this paper mill is still running, and the cogeneration plant needs to produce power and steam for the mill. Over the next couple of years, we're going to do some more tests, and we expect that for the SGT 400, in around 2 years, 2 to 3 years, we should be able to have all the tests concluded so that we can launch that unit commercially into the market for 100%. There will be probably another type of turbine that will get to the 100% commercially earlier, already by next year. But you will probably hear in the press once it is achieved. Another good example is a power plant in Brazil. This is a cogeneration plant with 2 SGT 600s. That's a 25 megawatt unit that is producing steam and power for a local refinery, and is using a fuel mixture that is coming from the refinery of around 40% natural gas and 60% hydrogen. And this unit is running commercially and baseload since 2022. It is achieving 25 ppm NOx regularly, and we even have an operation and maintenance contract. That means we are responsible to provide the power plant, the refinery, with steam and power. And in the last 2 years, it has run very well. In the peak, we were able to run this turbine at 88% hydrogen, but that was the limit that the unit could achieve. At 88%, the flak bash system said, that's my limit, and stopped the increased amount of hydrogen. A good example of already a very high amount of hydrogen being used commercially in a turbine, and not just for a few hours, but really baseload operation. Good example as well about testing is what we call the Zero Emission Hydrogen Turbine Center in Sweden, in the city of Finspång. That's where we manufacture our medium-sized turbines from 25 to 60 megawatts. At that size of turbines, we're still testing every turbine that leaves the factory. And so we have a test facility where all the gas turbines are being started up. And because we also want to test hydrogen, what I've done is we have put a complete hydrogen landscape over there. So we have added electrolysis, we have added hydrogen storage, also a few solar panels, that's not much, also some batteries. We have as well all the LNG facilities that we need to run on natural gas. And what we're using is in normal operations of the turbine test center where we're producing electricity, which maybe the grid doesn't want to use. We can convert that electricity to hydrogen and store that in the tank so that we have it available for the hydrogen test that we maybe do a couple of weeks later. And that has already been in operation since 3 years. And at least the amount of hydrogen is not sufficient to completely fill a turbine, but at least what we can do in these turbines is we do sector tests. That means we're running a certain amount of burners with hydrogen and the rest of the burners with natural gas. And that gives us at least a better feeling of what happens inside a real turbine if it's not just one burner test in a test cell, but really what happens inside a combustion chamber. I talked a little bit about NOx. You know that NOx is usually measured in ppm or milligrams per non-cubic meter. That means it's a relative concentration, what we measure. But, very important, we always measure the NOx referenced to dry exhaust and 15% O2 content in the exhaust gas. That's how emission limits for gas turbines are worldwide set. And as we're now switching to a different fuel, two things happen. The first one is with hydrogen, we get a much higher volume. We get a different amount of O2 concentration in the exhaust. And because hydrogen combusts to water, we get a much more water intake into the exhaust. And if we have to reference it to a dry exhaust and to 15% O2 content, both factors are unfortunately negative and lead to higher figures. And at 100% hydrogen, the figure is 37.2% higher compared with natural gas. And that is purely mathematical. Even with the same amount of molecules, NOx molecules in the exhaust, by the way we define NOx emissions, we get a 37% higher emission. And that is something that needs to be understood. We're currently in discussions with different regulators, both in Germany and the UK, about how can we in the future define NOx emission levels of power plants. And we're both discussing a fuel correction factor or changing the measurement unit instead of ppm to milligrams per kilowatt hour of energy output. That's something that's still ongoing. The UK is leaning towards a fuel correction. In Germany, we think about both topics. But I just don't want to leave this untouched. You have to know we have, when we talk hydrogen combustion, a slightly higher production of NOx because of thermal issues in the combustion chamber, but also this 37.2% effect purely on mathematics of how we have defined the measurement unit. So let's now look at the topic of retrofit of existing turbines. So far I've been talking about new turbines. That's easy to handle. Well, not so easy, but easier than with an existing turbine. But effectively what we're going to see is that we also have to look at the retrofit of existing turbines for several reasons. There may be some locations in the world where we might see blending of hydrogen and natural gas in the gas pipeline grid. It's not something that will happen in Europe. And Europe has made the decision to build a complete separate network of hydrogen and keep the natural gas network completely with natural gas. That means methane only. But there may be some other locations in the world that might see blended pipelines, and then every turbine connected to that pipeline system will have to use this blended fuel. Then we may see, we'll probably likely see, changes in legislation enforcing decarbonization of power plants. Think about what we saw already with EU taxonomy discussions, where we're limiting the amount of CO2 emissions of power plants to 100 grams per kilowatt hour in order to be considered sustainable. Something else could happen, and then the operator would have to add hydrogen so to achieve the CO2 emission limits. And then finally, if you look at the lifetime of a real power plant, 25 to 30 years for a combined cycle, if you build a power plant today and put it into operation in 2027, 28, this plant will still be in operation in the 2050s, where we're supposed to be completely decarbonized in the world. So for every new power plant in the future, we have to expect that eventually this power plant will have to be converted to hydrogen operation. And that is why we're really looking very much at retrofitting of turbines. And retrofitting turbines is not a straight process. We really have to look item by item. We have to really look into each plant, what are the upgrade requirements, what are the local regulatory requirements, operational requirements, how much hydrogen do we want to use. Then we have to do a due diligence of everything that has been installed, whether it's the turbine itself, but also all the auxiliaries. And then we have to analyze, well, what changes are required in all the different areas. And only then we can really make a decision on which changes are really required. Then we can prepare, upgrade the project, do proposals, negotiate, and then we can work, install, commission. We have to do a new commissioning of the power plant with a new fuel. We'll also need a few new performance tests because of different fuel, and also topics about certification of the plant, permitting, also something that needs to be looked at. So this is always going to be a project-specific evaluation. Technically, you can always convert any power plant to hydrogen. The question is, how much will it cost? And the higher the hydrogen content, the costs will probably skyrocket eventually. Think about what happens in the extreme case. First, you have to convert all the upstream equipment, everything that's upstream of the turbines, all the fuel gas system you have to probably change. You also need to change the burner, but that's the small part. You may have to retrofit explosion-proof protection into the power plant. That's a major topic. Ripping out all the electrical systems in the package in the machine house building and putting explosion-proof protection. Maybe you need an SCR in the future, which you may not have today. And that means cutting the boiler and moving it by 2 meters away, including the stack. And if you have very bad lag and you don't have sufficient space between the foundation and the turbine casing, the larger pipes may not fit, and then you would have to raise the turbine axis. So it can get quite problematic if you have not planned from the beginning for hydrogen operation. The areas that you have to look at in case of retrofit are more or less the same. We have to talk about obviously the burner. We may have to do a burner adjustment or an exchange. We'll have to add a purging system with nitrogen. We'll have to look at the fuel gas system material on the setup, and here we're going to see some changes. Look as well at H2 compatibility of plant auxiliary and peripheral systems. Flame control, combustion monitoring systems will have to change. Then fire protection, gas detection system. Obviously, we need hydrogen detectors as well. Then a big topic, gas group 2C, which means explosion proof of all the electrical equipment. Additional ventilation. Remember that hydrogen is a very light gas, so if you have a small leakage, it will tend to accumulate on the top, and with hydrogen between 4 and 72% concentration, you already have an explosive atmosphere. And because of the high flame speed, if you have an explosion of hydrogen, this is not an explosion or a deflagration that you see with natural gas. It is a detonation, and it can have very strong pressure surges. So it's a topic that you need to take into account. And then as well, all the systems, you have to look at permitting as well. You have to talk to the regulators. A couple of topics that you need to take into account. And because of all these topics, we have a concept that we call H2 readiness. And that is something that over the last 2 to 3 years became very important in Germany and as well in Europe. More or less became a standard. And I first want to explain the terminology. H2 readiness means that I'm building a new power plant, but the power plant is already prepared for a later retrofit to hydrogen. And that is something that means the power plant is not yet ready to operate with hydrogen, because that would be the H2 capability. That's the actual capability to run on hydrogen, but it's just I have already prepared the plant so that I can later retrofit it very simple with hydrogen. Important topic, because even in our company I see lots of engineers saying H2 readiness when they mean capability and the way around. So I really want to make sure 100% hydrogen readiness means the plant is not yet ready to run on hydrogen, but it's prepared for a later retrofit. And that means that everything that can be done beforehand when we build a new plant and does not really add too much cost, we rather do upfront, and we leave only selective topics for a later retrofit. That means, for instance, when we talk about the fuel supply system, that we have selected the right materials and the right sizes of the pipes from day one. We have as well additional space layout in the plant for putting maybe a mixing skid or a purging system later, and as well sufficient place in the pipe racks in order to lay down a pipeline for hydrogen as well. The gas turbine, obviously, the burner is something that we're going to change later once we really retrofit. But regarding fire and explosion-proof protection, I will have already explosion-proof from day one. Because the additional cost of an explosion-proof electrical system is not very much higher than a normal one, but if you have to change it later, it comes very expensive. HRSG as well, right materials. If I need to have later an SCR, I can already put a spool, so that I can easily then retrofit an SCR. Or I can design the SCR so that it also works then later with hydrogen. So INC and electrical, already gas classification 2C, and from a safety permitting, I can already prepare everything for hydrogen. So we're talking about a few percentage points of additional capex, but then later, when I retrofit it, it's very low disruptions and low costs. And that takes away lots of these issues of retrofitting costs and risks. A good example is a power plant that we're just building in Stuttgart in Germany. That's a cogeneration plant to SGT 800. The idea is this plant will operate with natural gas for the first 7, 8, 9 years, and then eventually will switch to hydrogen as soon as the pipeline is there and the amounts of hydrogen and the market design for operating with hydrogen is there. And it's one of the first turbines and power plants that was built 100% H2 ready from day one. So the plant will be easily retrofittable to hydrogen in a couple of years. In Germany, by the way, there is already a requirement in law that all new power plants have to be built 100% H2 ready. Same applies for pipelines, same applies for compression stations, same applies for LNG terminals. H2 ready is becoming a standard nowadays. There's a couple of examples of power plants that are currently being built or have been built with H2 already mined, and probably in the next few years this is going to increase because this is becoming a standard in the industry. So let's look now finally at some other derivatives. I explained before we have two different types of other fuels, hydrogen derivatives and the biofuels. Let's first look at biofuels. When we talk about biofuels, we have to talk about the different generations of biofuel. Usually what we know today of biofuels is generation 1. So these are fuels produced directly from crops like corn, sugarcane, or rapeseed. The big disadvantage of these fuels is that they compete with food production. And as such, they're not considered sustainable by governments. You get a decarbonization factor of 65 to 85%. You still have quite a lot of conventional energy being put into that one. So they are largely decarbonized, but they're not sustainable. And for the future, you cannot expect to run on first generation fuels. So you have to go at least to second generation, and these are fuels produced from waste feedstock or produced on non-arable land. That means they're not competing with food production. Examples are ethanol produced from bagasse, HVO from jatropha, which is a crop that grows on free terrain that you cannot use for food production, biodiesel from black liquor from the pulp and paper industry, or sustainable aviation fuel, Fischer-Tropsch fuels from waste oils. They are quite sustainable. The issue with these fuels are this limited potential. The amount of biogenic waste and non-arable farmland is limited in the world, and this is not going to solve all the problems of energy in our planet. But it is a very attractive fuel to decarbonize, so that's why we're looking very seriously at. Third and fourth generation are produced from algae. This is still on a lab scale. Costs are still very high. Reliability is not yet there. There may become eventually a topic, but it will still take some time. So we keep that in watch, but for the time being, biofuels is mainly for our second generation, and that is something that we need to, we're already doing. And a couple of roadmaps that we have here, we're really looking at biodiesels, especially HVO and Fischer-Tropsch fuel. FAME is another interesting biofuel. I'm going to talk about that in a moment. And methanol and ethanol, which could be both biogenic or could be as well a hydrogen derivative. So let's look at the different roadmaps. This is a roadmap showing the activities on the small and the medium-sized turbines that we have. Medium-sized, you will see a higher activity on these decarbonized fuels simply because from the size perspective and also because they are quite often used in islands. They are more prone to be used for testing and decarbonized earlier compared with large turbines. But you see that we have been working not just with hydrogen, but as well with other fuels like HVO, FAME, ethanol, and going to show you a couple of examples. The first one is the use of HVO, which is a biodiesel, is hydrogenated vegetable oil. This is a very attractive fuel because it's a fuel that is very similar to conventional diesel or light distillate oils. You see here HVO is the gray line. This is a picture of distillation curves over the volume and temperature levels. So it behaves very similar to a diesel. It's nearly easily switch over from diesel to HVO. We have done a couple of tests at a power plant in Sweden with SGT 800 power plants with very good results. And we've just begun commercial operation of a peak load plant in Stockholm, also in Sweden, with an SGT-800 running on 100% HVO. So HVO is a very attractive fuel. Disadvantage, there's not a very large market for it, and everybody wants to use it because it's an easy drop-in for diesel. There's another biodiesel, which is called FAME, fatty acid methyl ester, often produced, for instance, from rapeseed. This is a different fuel, a little bit more difficult to burn because it differs a little bit more from a biodiesel. And it also has the disadvantage that it is chemically not stable. So over time it degrades, and many liquid fuels you want to have as stored on a large tank, maybe only for some secondary fuels. And obviously every fuel that you want to store for lots of weeks or months in a tank has to be stable, and FAME is not, while HVO is there. Examples of these modern biofuels, I've talked about Stockholm and Göteborg. We have as well done tests on biomethanol, which I'm also going to explain. And there are lots of other biogases as well, biomethane, usually something for smaller turbines, not going to be a solution for large generation, but occasionally for smaller turbines, landfill gas is an attractive alternative fuel as well. Stockholm, I already explained a little bit. This plant went in commercial operation last year and will not run many hours a year because it's mainly for peaking applications and a little bit of CHP, but nice example of 100%, or nearly 100% decarbonized. So let's look at methanol. Methanol is a very attractive fuel, both as a biogenic and as well as a hydrogen derivative. It has some big advantages because if you compare methanol with a conventional fuel like diesel or kerosene, it has some advantages. Obviously, you can get a reduction of CO2 emissions. Interestingly as well, you have much lower NOx emissions if you burn methanol compared with diesel or light distillate. And you also get a much lower emissions of SO2. Usually methanol is SO2 free, sulfur free. You have less smoke, less PM. It's also easier to combust, so it's more stable to combust, more stable to start a turbine. We have done a couple of demonstration tests on an A20, which is an aeroderivative turbine. In this case, it was run with biomethanol, but 100% methanol could be as well comparative with e-methanol. We have demonstrated safe operation from startup to full power. Also, the auxiliary systems we had to do a couple of changes, but were not so critical. Some materials of glands and sealings needed to be adapted, but in general, it's easy to handle liquid fuel at atmospheric conditions, ideal alternative to diesel. We know how to deal with methanol, and taking into account that maybe in the future the shipping industry will move more and more to methanol as a shipping fuel, and also other industries were going to use more methanol as a direct substitute of a liquid fossil fuel. And with the existing market for methanol that there is today for the chemical industry, and methanol being a very simple synthesis from hydrogen, so there will be a large fluid methanol market in the future. Methanol could be a very attractive fuel for gas turbines in the future. Still a very expensive one, more expensive than hydrogen, but if you cannot use hydrogen, methanol is really a very attractive fuel for those locations where you cannot get access to a pipeline, islands, tropics. And we're already in good discussions with several customers for these sort of projects. These are the examples of the tests that we did in Aberdeen with the local university, running an 820, which is around 15 to 20 megawatts aeroderivative turbine, formerly called the Industrial Avon, maybe. And we got an 80% reduction in NOx, and this was diffusion mode, by the way. And we also got a higher power output compared with the original fuel, which was in this case kerosene. So very good, interesting fuel. Now let's switch to ammonia. Ammonia is a compound that is quite interested from a hydrogen transport vector perspective. The idea of use of ammonia is you produce that in areas where you have best conditions for renewable energy. And Oman definitely belongs to these countries. So you produce renewable energy, you put that into electrolysis, you have the ammonia synthesis, and then you ship it to the country of destination, which could be Germany, Japan, US, you name it. And then you can have three options how you can then re-electrify that ammonia. The first one is you do a direct combustion. I'm going to come that in a moment. Or you do a central cracker, which means you're separating the nitrogen from the hydrogen centrally at the port of destination, and then you fill the hydrogen network, pipeline network, and then you have a conventional hydrogen power plant. The other option is you bring the ammonia to the power plant, and you have a local cracker integrated with the power plant, and then you produce you run the power plant, the gas turbine, with cracked ammonia. So looking first at direct combustion. I talked about hydrogen being a difficult fuel. Well, ammonia is even more difficult and more nasty. And this is a slide showing all the issues that we see with direct combustion of ammonia. If hydrogen was extremely reactive, ammonia is exactly the opposite. You have a very low flame speed. Again, a factor of 10 lower than natural gas. You have a low heating value. You have a low combustibility, high ignition temperature, high ignition energy. That means you need a complete new burner design for ammonia. And these burner designs, by the nature of ammonia, will probably not be fuel flexible. That means you will not have dual fuel options. It will just be an ammonia burner. With hydrogen burners, the goal that we have is to have always the capability of running both natural gas and hydrogen. Even 100% hydrogen turbine means we can still run on 100% natural gas and any mixture in between. And we can also add, for instance, a methanol burner or a diesel burner. That could also be a possibility. With ammonia, it's not possible. Then probably one of the biggest issues is ammonia is a toxic compound. And unfortunately, under atmospheric conditions, it's a gas. It's being handled as a liquefied cryogenic fuel. That means that as soon as we have a leakage, you get a toxic vapor of cloud. That means first you need significant EHS requirements in the plant, safety requirements in the plant to protect your workers, but also you need to avoid any release of unburned ammonia outside of the power plant fence. And that includes as well, under all operating conditions, think about trips, think about failed starts, or think about flame out events, especially at a fuel which, because of the low flame speed, is very prone to flame out events. If you have an ammonia power plant running on 100% ammonia and you have a flame out event, until the flame detectors realize the flame is gone, the computers process that information, send the signal to the shut-off valves. Shut-off valves close, you have around 800, 1,000 milliseconds of full ammonia load that goes unburned through the stack. And with ammonia, already from a single-digit ppm, you can already smell it. And single-digit ppm is, by the way, also the current emission limits for unburned ammonia from the SCR. And only 5,000 ppm is already a lethal dosage for a human being for a 5-minute exposure. So very serious topic, and for the time being, we see this as a very, very serious issue. And then ammonia has the issue of NOx and N2O emissions. Ammonia has fuel-bound nitrogen, and as soon as you crack that molecule, you have a nitrogen radical, which immediately goes to the next oxygen molecule, combines itself and produces NO, NO2, and also N2O, which, by the way, is one of the largest greenhouse gases, in a very high manner. You can get NOx emissions up to 4-digit ppm, which is significant. So you would need complex multi-stage SCRs and as well N2O catalysts. Makes it quite complex from a plant perspective. And then as well, another topic to look at is fuel corrosivity. Ammonia in contact with steel produces nitridation. So you begin to corrode the materials. And that also applies for nickel. And remember that in the turbine is quite full of nickel materials, especially in the hot gas path. And so long-term maintenance costs for ammonia plants is something that we have to look at. Some of them can be managed with a change to more noble materials, but still a big question is long-term effects of corrosion in ammonia power plant. And then finally, from a pure strategic point of view, if we look at the amount of R&D efforts that we need to develop ammonia burners, it's at least as expensive and takes as much time as developing hydrogen burners. There is a limited market size. We expect that probably only 20–30% of total turbines sold in the world may be looking at ammonia. And if you can imagine, even we as a company have limited resources, both financially and as well people-wise. We don't have sufficient combustion engineers to develop all those combination of 10 different fuels, 15 different turbine frames. And there is an alternative, which is called cracking. That is why, for the time being, although we're looking at direct combustion as well, we're more focusing on cracking as a solution to re-electrify ammonia. This is an example of some of the tests that we did together with some universities using our burners. These are the technical comparison between CH4, natural gas, hydrogen to the right, and ammonia to the left. You see heating value is highest with hydrogen, lowest with ammonia. Flame temperature is lowest with ammonia, highest with hydrogen. Flame speed, 0.07 compared to 0.37 and 2.91 on hydrogen. So it's a really big issue in order to ensure that the flame remains stable and doesn't blow out. And ignition temperature is much higher. You can, if you run with ammonia, if you add hydrogen or methane, you can improve the combustion stability. It helps at least to keep the combustion more stable, but you still have the issue of all the NOx emissions that you have to manage. Looking at the NOx emission, depending on the equivalence ratio, you can see that the NOx emission levels can really get to a significant quadruple-digit ppms. And that needs to be managed. You can manage it by having a different burner type, where you begin with a very rich combustion, then quickly switch to a very lean combustion. But again, this is a complete new burner type and will not be able to be run with other fuels. And we've done really examples, combustion tests with a burner of an SGT 750. You can really see here, depending on the equivalent ratio, the NOx emission levels, 2,500, 3,000 ppm, so factor 100 compared with conventional gas power plants. Not a very nice fuel. And there is obviously, there is an alternative, and that is the cracking. Cracking means you put a cracker in front of the power plant, you separate nitrogen from hydrogen, and then you have effectively a power plant running on 100% hydrogen. Big advantage of hydrogen, you can easily store it. So a tank of this size, and you see this size, these tanks of ammonia very often in chemical plants, would give enough fuel to run an SGT 800, which is a 57, 60 megawatt gas turbine for 3 months. They're much easier to store energy locally compared with hydrogen. And we have done tests as well with cracked ammonia on an SGT 800 burner with very good results, by the way. Even when we talk about cracked ammonia, what we're putting into the burner is not 100% hydrogen. It's a combination of hydrogen and nitrogen, so separated molecules, 75% hydrogen and 25% nitrogen. And that is interestingly much easier to combust than 100% hydrogen, because the nitrogen reduces a little bit the reactivity of this fuel. And we've done these tests. At least the tests were so good that we immediately released 50% ammonia, cracked ammonia with natural gas commercially. And we expect that in the next few years we're going to get as well the 100% commercially available. We're already talking about customers in East Asia about the use of also large turbines, 9000 HL, running on 100% cracked ammonia. So the idea is then for use of ammonia that we have an ammonia tank, we have a cracker where we have more or less a full conversion. Full conversion means the amount of remaining ammonia slip is rather low. We may need a membrane separator to get the remaining NH3 out. The point is, whatever rest of ammonia you get into the power plant, you will produce additional NOx, and you have as well the safety issue. And then the idea is to combine the power plant with the cracker in a more integrated way, so that you can, for instance, use excess heat or low quality heat from the water steam cycle, for instance, to run the gasifier of the cracker. You can, obviously, the larger the plant, the more possibilities you have for integration, and that increases significantly the amount of efficiency. And at the end, you may have just an efficiency loss of 2 or 3% in the best case, compared with direct combustion. You will still need an SCR because we're talking about maybe 50 ppm of NH3 that still remains in the gas. So you will need an SCR to reduce the NOx emission. But at least the power plant itself will be a rather safe location where there's nearly any ammonia left. You keep all the ammonia in the cracker, so it's very stable. You don't have issues with trips and fail starts with ammonia emissions. And that is what we recommend today for those customers that are interested to use ammonia as a fuel. This is nothing for Oman. Oman, I would rather see the use of hydrogen long term. So, last slide. As I said, gas turbines, combined cycles, today running with natural gas, will still have a reason to be there. It's not an old technology. We expect combined cycles to be the main technology to cover the residual load. So all those hours of the year where there is not enough solar and wind in the system and where batteries cannot fill up, then combined cycles running on a decarbonized fuel will close the gap with the demand. And obviously we have to run it on a decarbonized fuel, and hydrogen is the most attractive fuel, and 60–70% of all the future power plants will run on hydrogen as a decarbonized fuel. For the others, we expect biogenic fuels and hydrogen derivatives to be used as well, mainly for those areas where there's no access to a hydrogen pipeline, islands, and the like. And yeah, we're working on all these different fuels. with hydrogen, we're already quite advanced. With all the others, we have done a couple of tests. Some of them are already running commercially, but as I said, we have 15 different frames, 10 different fuels to consider. That's 150 combinations, and over the next couple of years, you're going to see more and more of these cases being released commercially. And when we talk about e-ammonia, our recommendation is to go to cracked ammonia and not a direct combustion. So that concludes my presentation. Thank you very much for the attention. Now we still have some time for some questions and answers. Yes, over there.
Considering the scenario of converting cements, for example, gas turbine from fuel gas to hydrogen, and for example, B94.3 as plus, what will be the impact on the heat efficiency in terms of
Yep.
power output and heat rate?
Yep.
Operating hours, any limitation in terms of the outage intervals? For example, now 33 kEh.
Yeah. These are questions that we cannot yet fully answer today. The goal is to get to the same maintenance intervals as we have today with natural gas. That we can only show, obviously, with more experience on running on hydrogen. Regarding the effect on performance, efficiency, and power output, I said it's not easy to develop hydrogen burners, and what we're doing at the moment is we first want to do the development step by step. We first want to get into 100% in a safe way, accepting an introductory performance rating. That means lower power output, slightly lower performance as well, and once we achieve the 100% hydrogen combustion, we're going to work on the performance, increasing the performance back to more or less the same levels as we have today with natural gas. That's the goal. And if you look at a complete combined cycle power plant with some very small effects where we're going to see a small difference, long term we expect the same performance level. We still have the issue of higher water exhaust content in the exhaust gas. That means we have to slightly increase the temperature of the exhaust of the stack temperature to avoid dew point corrosion. So, but that's 10 degrees approximately. So we're losing a little bit of energy in the water steam cycle, and we have a little bit of more ventilation in the power plant because of explosion proof. So slightly higher auxiliary load demand, but in general, combined cycle efficiency maybe 0.2, 0.3 deficit long term. But that's the goal, to get to the same levels. And once we achieve the same performance, only then we're going to work as well on NOx emissions. So we're going to do step-by-step development. First 100% hydrogen combustion, then we'll work on performance, and then finally on the NOx emissions. It will take several years to get there, but we're quite sure we will be ready by the time the hydrogen will really be used in a fuel. This is not something that's going to happen in the next 2 or 3 years. We're talking about the 30s and the 40s.
Thank you.
Yep, was another question.
Yeah. See, looking into the hydrogen upcoming business, still people are discussing between these two vectors of ammonia and methanol. So how do you look towards the acceptance of methanol-based power generation versus maybe the cracked ammonia, or what best option? Because hydrogen, we are not going to transport hydrogen to the long distances, maybe to Europe or Japan.
Yep.
So how you look towards the acceptance?
Yeah, it depends on the location, and depends on the hydrogen economy in that country. It's easier to synthesize ammonia than methanol. Technically, it's the same. The issue with methanol is you need a sustainable source of CO2, and that's not easy to get. So it's probably first easier to transport the energy as ammonia into, let's say, Europe, instead of using methanol. What I do expect is that we're going to see the use of methanol for those applications where we really want to have the methanol as a compound, for instance in the chemical industry, where we want to use it as an easy fuel. Ammonia will always be a very complex fuel to burn, whether it's in the industry or in turbines or in engines. You always have the same issues of safety and NOx emissions. So for those applications, we're going to see methanol. And you have to look as well, what are other users of hydrogen and ammonia? So in a region like Europe, where we expect to be hydrogen deficitarian, we need to import hydrogen. Some of the imports will be done through pipelines from Morocco, Algeria, Egypt, and the like, but there will be as well hydrogen being imported as ammonia, in which case we will need a cracker, a central cracker at Rotterdam or one of the ports of entry. So we're going to fill the hydrogen pipeline, and in those cases, the use of ammonia is probably as a fuel for turbines not so interesting. With a small exception, at the cracker itself, there might be an attractive opportunity to put a large turbine, because the integration of a turbine with a cracker makes thermodynamically lots of sense. But in countries like Germany, all Europe, I do not see ammonia as a fuel for turbines. I do see it in Japan, in South Korea, in Taiwan, where they will never have sufficient hydrogen pipelines or amounts of hydrogen. So those countries will see ammonia, also in the tropics, and mainly for larger generation, because of all the different difficulties with ammonia. It's rather central generation, while when we talk about smaller islands, 50, 100 megawatts, you probably will go for methanol because it's easier to manage, easier to handle. So that's my vision. But if you ask me, maybe in 12 months, I will give you a different answer. It's still under consideration.
So what I think about it is that methanol is basically difficult to manufacture in comparison to ammonia. Yeah, but once if we have decided to go for methanol, like I am referring to the coming up projects in Oman.
Yep.
Because still discussions are going on, and every project is having their different vision of going one for ammonia or for methanol. So once I have imported methanol, then methanol as energy, it is a better option.
Methanol is easier to handle. Methanol has a very high attractiveness, and I would not just stop at methanol. Probably one of the most attractive compounds is sustainable aviation fuel, because that's the first market where I do expect mandatory requirements for blending, and where we're going to see a real ramp up of market demand. And I would expect that sustainable aviation fuel will be produced as well in the country of production.
Yeah,
so there's it doesn't make any sense to put the wind parks and the PV panel here, produce the hydrogen, produce methanol, and then ship the methanol to Germany to produce stuff. You would rather do everything here.
That is also one of the vector which we will be looking
Exactly. So sustainable aviation fuel is very attractive, and methanol especially for the shipping industry, and as well for conventional use of methanol that we have today in the chemical industry. They are also probably quite attractive. We're going to see some examples of power generation as well with methanol. I do expect more the smaller sizes, not the very large central generation, especially for islands. It's quite attractive because islands today have a generation based on diesel and heavy fuel oil with engines, low efficiency, extreme high CO2 emissions, high costs, and a switch to a decarbonized fuel like methanol makes probably much more sense in islands rather than in central grids where we have other options as well.
Thank you.
Was a question as well on the back? Can you use the microphone so that everybody can understand?
It might be a question out of what we discussed, but it was one of my interest, which is it's related somehow because it's another way to produce hydrogen, which is a photocatalyst. I've worked on it, and when I was in for my project, for my final project, and with like photosynthesis for develop photocatalyst, which is solar-driven hydrogen production, which is, as far as I know, it's something under research right now. But I would like to see what is your, considering of course your existing experience, what is your opinion about it?
There are several ways of producing hydrogen. At the end, what counts is what is the cost of hydrogen, of the final hydrogen, and what is the associated CO2 footprint. With photocatalysts, you could have a very high decarbonization rate. The big question is, will it be cheaper than electrolysis? And that is the big question. Hydrogen will be a commodity. And at the end, there's only one thing that counts, apart from the CO2 footprint, and that's the cost per ton.
And do you consider it like a developed technology to adapt, or it has more challenges?
No, definitely, and we're going to see significant amounts of new technology breakthroughs in several different types of technologies to produce hydrogen. We're going to see as well, there's also some other options of using maybe CO2 catalyst to produce directly hydrocarbons out of hydrogen. And that's also something where we as a company are looking at, which may be a much easier way of synthesizing than maybe sustainable aviation fuels compared with Fischer-Tropsch or a methanol to kerosene synthesis, because all these synthesis processes, they look easy on the paper, but they are effectively large refineries. So it's a huge amount of equipment that we need to do a synthesis project. Methanol is easy to synthesize, but until you have sustainable aviation fuel, it's 5 times the amount of capex. It's a large refinery that you have to build effectively with Fischer-Tropsch and additional refining. And if you have other options of producing these energy vectors, I'm sure more will come. But remember always, this is a commodity business, and at the end, we're going to see pure discussion about where can I get my energy cheapest from.
About the cost then.
Yeah, cost is the most important factor in this business in the future. And that is why for a country like Oman it's so important to embrace on these new technologies, because Oman has the big advantage of having excellent PV and excellent wind conditions as well. And there will only be a few countries in the world where you will have such good conditions. That means Oman is one of the best countries to produce hydrogen at very cheap costs, and as well methanol and ammonia at very cheap costs. Transporting the liquid compounds is easy. It doesn't cost much. And that's why I'm going to say what I also said in the past. Germany will not be a country where we're going to produce large amounts of hydrogen and e-fuels and the like. We're going to use it as well because we need to have the electrolysis as well to cope with the surplus of energy. But most of the green energy that we're going to consume in Germany will be imported. Especially methanol, SAF, will all be produced in other countries like in Oman, Chile, Mexico, South Africa, Namibia, Australia. Those are the countries. And Oman is definitely one of the best suited locations in the world. It's really about where can I get the energy cheapest from. And it's the same as with conventional mining industry or oil and gas industry. At the end, you have a world market price for green energy, for hydrogen and ammonia and methanol, and whoever can produce it cheaper will earn more money, will have higher profits, and can also operate when the price goes down in the market. Any more questions?
First, thanks for the presentation. It's pretty insightful. I have one question in regard of using ammonia cracker. Isn't it's more intensive process? So how would that really works?
Yeah, the cracking is an endothermal process. That means we're using energy to crack the molecule, but we're mainly using the energy first to gasify the ammonia. Ammonia comes as a cryogenic fuel at probably minus 40 degrees C, so you have to heat that up to around 600, 700 degrees in order to crack the molecule. But if you use, for instance, cheap, free heat from the combined cycle power plant, think about the cooling water. You need cooling in a power plant. At the same time, you need the same amount of temperatures in the cracker for gasifying the ammonia. So use the cooling water to gasify the equipment. And if you can then use maybe some steam from the water steam cycle to give that to the cracker, and at the same time, the heat that you get, you put back into the boiler, then you have a rather optimized configuration, and instead of 15 or 20% energy losses, you can reduce that to 3 or 4% losses in total. So by integration, you get a much higher total efficiency. Obviously, it's still, you have the issue of some of the energy losses that are you cannot get through, and you have a much higher capex. A cracker is as much capex as the power plant itself. That is a disadvantage that you have to come up with. With direct combustion, obviously, you would not need a cracker, but you have much more costs as well in the NOx emission levels, in safety requirements, and from a risk perspective, I'm not yet convinced in direct combustion. And that's why if you can do hydrogen, you go hydrogen. It's only for those few countries that cannot get access to hydrogen through a pipeline, like Japan, Korea, Taiwan, tropics, and the like. Okay, if there are no more questions. Oh, there's one question over there.
Hello, I'm Siti from EGI, based in Berlin. So I just have a curiosity because you were talking about hydrogen as long-term storage in Europe since it's seasonal, and there are longer periods where I guess solar and wind don't blow as much. But for a country like Oman, I was just curious because if you talk about export, then you also need investment on infrastructure. But if you talk about storage to manage the intermittency of solar, for example, I believe that the reconversion to electricity will cause a lot of losses, right? From hydrogen to electricity again. So I just wanted to know your point of view in terms of the econs behind it, like what kind of strategy should be adopted in such a country?
Well, the idea is, as I said, whatever you can do with electricity storage as a battery is always has an advantage, because with battery you have a cycle efficiency of 90–95%, so that's very high. The big issue with batteries is that the cost of the batteries increase with the amount of kilowatt hours stored. And if you go to 3, 4, 5 hours, that's probably the limit at what we see today and what you can manage. If you need a longer period of storage, batteries will get less and less attractive. Then you have to look into flow batteries maybe in the future, pumped hydro as well. But if you really want to go into days, weeks, months, and seasonal storage, at the moment you need a chemical storage, and that's hydrogen. We have the disadvantage of this huge efficiency losses, but it's the only possibility to do seasonal storage. Yeah, one additional question here.
In case of the hydrogen turbine, telling us that the buy is to be huge.
Yep.
Thank you. The buy will be very huge, and the infrastructure for the existing power plant should be upgraded.
Mm-hmm.
It is in liquid or in gas condition, the hydrogen?
Well, hydrogen will be used in the future mainly as a gaseous fuel. We're going to use hydrogen in the pipeline system as a gas, compressed gas, probably around 180 to 100 bars. That will probably be the pressure level of hydrogen pipelines. When we talk about cavern storage, we're going to see 200, 300 bars likely. And the use of liquid hydrogen will be limited only to those cases where we cannot really get access to compressed hydrogen. Definitely not in the power plant business. We might use it maybe to transport hydrogen via truckload as a liquid hydrogen. Maybe that's a possibility. Long-term use of liquid hydrogen as a carrier is also possible, but we have the issues that we're losing 30–35% of the energy content for the liquefaction, and then we have a boil-off, which is around 0.5 to 1% a day. So you cannot really store that for longer periods of time because it disappears. It gasifies again. So only for very limited possibilities liquid hydrogen. Otherwise, we're talking a gaseous fuel with a low volumetric energy density. That's the disadvantage. On the other hand, it's a very small molecule, and we can use higher velocities in the pipeline as well. So the capacity of a pipeline of hydrogen compared to the same pipeline running on natural gas is around 80 to 90%. So we're very close. Maybe a little bit of smaller capacity, but we can nearly transport the same amount of hydrogen through a pipeline as with natural gas.
Thank you. Thank you.
Maybe one last question. In countries with high renewable energy resources, like Oman, wind and solar, unfortunately they are not rich of water. And we need a lot of water to produce hydrogen. What I have in mind is approximately 9 liters per kilogram.
How do we do? Yeah, exactly.
Any idea about that?
Yeah, you need around 10 liters per kilogram of hydrogen produced, and that water obviously disappears. Usually in electrolysis, you need demineralized water. And in countries like Oman, with a lack of fresh water, the only way to go is desalination. And desalination, obviously, you need a reverse osmosis plant. But if you make all the maths, you will find out that the total costs of hydrogen compared with use of fresh water just increased by 3 or 4%. Not much. And remember as well, reverse osmosis works with electricity, and electricity is something that you have for a very low cost here in this country. So you would run the reverse osmosis plant every time you have sufficient excess energy at nearly, I wouldn't say no cost, but very low cost. And in total, you have a little bit of more capex that you have to invest, but on the levelized cost of hydrogen, it's only a few percentage points additional cost. Still more attractive to produce the hydrogen here with desalination than to produce it in an area where we have fresh water, but less conditions for renewable energy.
Yeah. Thanks for the answer. 3 to 4% is
it's
what I'm most
looking for. That's what we see worldwide. Obviously, it's the medium latitude levels where we have best conditions for renewable energy. The subtropics where we have wind and PV, or the very northern and southern hemisphere where we have lots of wind. In those areas we have sufficient water, but in the subtropics, obviously, we have all the desertic areas in the world, and here all the plants will use desalination. There will be obviously an issue. You cannot do hydrogen production in Mali, Chad, or Nigeria. That's probably not possible. But most of the cases, the next ocean is not very far away. So you would put the electrolysis and the water desalination to the ocean. In any case, you need to be there because if you want to export it, you need a ship, you need a harbor.
Yeah, but nowadays, the model which we will be bringing is mostly putting electrolyzers along with the solar hydro.
Yep.
Not on the seashore.
That's correct. Yep.
There is a balance between whether I need to transport electricity
exactly.
or I need to transport hydrogen.
Yeah, it's always cheaper to transport a molecule and not an electron. Depends on how far your wind parks and solar plants are. In Oman, I would expect. Yep.
40 to 50 kilometers.
Exactly. That's around the area.
We are having good PD and night.
Exactly. Yeah. So if you have a city like Oman where you really have the wind and solar very close to the coast, you would do that in the location.
Transport water up to there.
Yeah. Yeah. It's always important to understand to transport a molecule is always cheaper and more efficient than to transport an electron. Okay, if there are no more questions, I would like to thank you very much. This concludes the session, and this concludes as well the Power Talk. So thank you very much for your attention, and have a nice and safe trip home.
And we will take a group photo if everybody can come forward. Yeah?
For the few people that are still here.
Yeah.